Okay, so let's take a look at question 3 from the 2010 scholarship paper. Um, this is question 3a, and I'll do a separate video for question 3b. Um, this is all about Zwitterions. Now, Zwitterions, I thought I had an idea of what they were about just from my university chemistry, which was quite a long time ago. So I had to do a bit of background research to fully understand this question. Nicotinic acid is a compound that can act both as an acid and as a base. And when dissolved in water, that exists as a Zwitterion, as shown in the diagram below. So this is Zwitterion right here. And there's two pKa's because you have two possible hydrogens that you could remove from that compound depending on what state it is in. So the question here is predict the pH range of a solution of nicotinic acid in water. Justify your answer using the Ka expression, and the second bullet point, include in your answer the structures of the conjugate acid and conjugate base of nicotinic acid, and assign the pKa values given above to their functional group. So we have to pick, there's two functional groups here. There's the amine functional group and there's the carboxylic acid functional group. And we need to decide which of these pKa values is linked to which of those functional groups. So what I did was, as I said, I did a little bit of research, and this is what I've copied down now, and this is courtesy of Wikipedia. So all this information is from Wikipedia. So unlike simple amphoteric compounds, for example, water or hydrogen sulfate, that might only form either a cationic or anionic species depending on external conditions, a Zwitterion simultaneously has both ionic states in the same molecule, so it can have a positive charge and a negative charge essentially in the same molecule. Amino acids are the best known examples. These compounds contain an ammonium and a carboxylate group. So right here, carboxylate group and ammonium group, and can be viewed as arising or not. So that's the carboxylic acid group, rather that's the amine group. And then when they deprotonate or swap protons around, you get the carboxylate group, which is there, and the ammonium group, which is there. So they can be viewed as arising via a kind of intramolecular acid-base reaction where the carboxylic acid donates its proton to the basic amine group. The amine group deprotonates the carboxylic acid, and this is known as tautomerizing. And as a result, you get a Zwitterion, which has both the positive and the negative charges within the same molecule. Now, what we're given here is we're given this Zwitterionic form for nicotinic acid, so you can see it has a negative charge right there and a positive charge right there. We have to talk about the reaction, the two reactions that this Zwitterion can undergo with water, where it acts as an acid or as a base, and that's its amphoteric nature. And then we need to relate these pKa values to the two functional groups and then to the Ka expression for this acid. So this is what we're going to do. So here's our Zwitterion right here. I just have this up at the top so we can refer back to that. There's two scenarios that we want to consider. The Zwitterion acting as a base and then the Zwitterion acting as an acid. So acting as a base, first of all, we start off with our Zwitterion. I'm just using this circle because that can show the three double bonds which are in a benzene ring or an aromatic ring. So we're starting off with our Zwitterion, two charges, negative and positive. And then if we reacted with water, we can set up an equilibrium there depending on the pH. All of these, the existence of all of these species is pH dependent, and that's what this question is really getting at. Then you're going to form the conjugate acid right there. That's the conjugate acid because you could lose this proton if the pH changes, plus hydroxide ions, which makes it a basic solution. So that's it acting as a base. Then acting as an acid, so we just use red color for that. We're starting off with the same Zwitterion, same charges, but if it's acting as an acid now, that means it's a proton donor. So again, this is pH dependent, but if the pH is right, then it will donate that proton from right there to your water. And so you'll end up with just neutral nitrogen down the bottom there, and then your charged carboxylate ion at the top plus H3O plus. And that there would be your conjugate base in that case. So the question did ask us to identify the conjugate acid and the conjugate base, and now we need to assign pKa values to the different functional groups. So what we need to identify within these two equations is are the two acids which are possible for this Zwitterion to form. So there's the conjugate acid right here, where it could lose this carboxylic acid proton, or there's the carboxylic acid, there's the conjugate acid situation down here, where it could lose this proton from the amine group right here. So carboxylic acids are much more acidic than the proton which is on the nitrogen right here. So it should have the larger or the smaller pKa because it should be easier to remove that. So the pKa for this one is 3.0, whereas the pKa for this proton to be lost right here is 4.9. So this basically is so I hope I said that correctly. So the pKa is 3.0. So the smaller the pKa, the larger the Ka, and therefore the better the acid. So the carboxylic acid group has a larger Ka or lower pKa value of 3.0, whereas the conjugate acid down here, which would need to lose this proton from the nitrogen, which is very difficult. You need a pKa of 4.9, which would mean a smaller, Ka, so therefore a weaker acid. So the presence of these two species is pH dependent. So the first situation to consider is if the pH is greater than the pKa of 3.0, then that means this proton can come off, and therefore the Zwitterion would dominate or would exist. Okay, so the Zwitterion would exist. If the pH is less than a pKa of 3.0, so if the pH is less than 3.0, then this proton would stay there and the conjugate acid species would dominate in solution. Having said that, if we go to a pH which is greater, so if we go to a pH which is greater than 4.9, then this proton right here will come off and the conjugate base species will exist. So the conjugate base species would dominate. And then if we keep the pH between 3.0 and 4.9, then that means, so then if we keep the pH between 3 and 4.9, then the Zwitterion species will be able to exist or dominate. And that's what we're looking for there. So the other thing to talk about here is the use of the Ka expression to explain which of these species will dominate in solution. So a general term we can write for the Ka expression is that the Ka expression is going to be equal to the concentration of H3O plus times the concentration of the conjugate base over the concentration of the acidic species. So the acidic species in the first equation is your conjugate acid right there, and if your acidic species is greater than the Ka is greater than 1. So what we're doing here with this Ka expression is we're relating the conjugate acid in the first equation to the concentration of acid. Now, if that concentration is large, so in other words, if we want the conjugate acid to exist, we want to have a Ka which is less than 1, because if he's a large number on the bottom, we'll get a Ka expression which is less than 1. And we also want the pH to be okay, so I'm going to restart that explanation because I wasn't doing it very well. We have to consider both equations, so equation 1 and equation 2. I've annotated which species each compound represents. So in the first equation, the Zwitterion is represented by A minus, which is our conjugate base. The conjugate acid is represented by our HA species in brackets, and the Ka expression for that would then be the concentration of H3O plus, so you could figure that out from the concentration of OH minus, times the conjugate base, which in this case is our Zwitterion, and all over the concentration of our acidic species, which is the conjugate acid species in this case. Now, the exam question was asking us, how do we work out the pH range for our Zwitterion to be the major species? So our Zwitterion in this case is the A- species right there. So that we want that species to be large, and if that's going to be large, then the Ka value is going to be greater than 1, and we want a pH to be greater than 3.0, because if the pH is greater than 3.0, as I said already, then that will drive the conjugate acid back to the conjugate base, which is our Zwitterion. If we take a look at the second equation, equation number 2, when it's acting as an acid, again, we want to preserve our Zwitterion, and that's the intention of the question. So to preserve the Zwitterion with the second equation, then the Ka expression can be written the same way again. So the hydronium ions in this case are there. The conjugate base, which is here, and that's not the species we want in this case, all over the acidic species, which is our Zwitterion. So to preserve a Zwitterion in the second case, we want to have a large concentration of the Zwitterion, so the Ka will be less than 1, and the pH should be less than 4.9, because if the pH is less than 4.9, then we cannot remove that proton, so we preserve the Zwitterion. So this is where we arrive at our conclusion that to preserve the Zwitterionic state, there must be a pH within the range of 3.0 to 4.9, and that to preserve the Zwitterion. Now, the second part of question 3, part A, is just a simple relationship between pH and pKa at the midpoint of a buffer. So an aqueous solution of nicotinic acid is titrated with sodium hydroxide. So this can be considered a weak acid strong base titration. Predict the pH at the center of the buffer region, which is the midpoint pH, and justify your answer. Well, hopefully you remember from level 3 titration curves that at the midpoint, the pKa of the weak acid should equal to the pH. So the pKa of the weak acid species, what we're talking about here is we take our Zwitterion. We still don't know which pKa to choose just yet, but we draw our Zwitterion, and we're reacting it with a strong base, and then we're going to form, the only thing that's possible is the base is going to remove that proton, so we're going to form this version of the ion, which is the conjugate acid. Not the conjugate acid, the conjugate base, of course, because it could accept a proton right there. So from the Zwitterion, you want to form the conjugate base, because of course the Zwitterion is acting as an acid in this case because you're reacting it with a strong base, and you form the conjugate base, which is that plus water. So this is the only proton left to lose if starting with a Zwitterion. So the pKa of that must be is 4.9. Therefore, the pH must be equal to 4.9 at the center of the buffer region, or the midpoint. And that's your explanation for that. So the pH is equal to the pKa of a particular proton that's trying to remove at the center of the buffer region. And that's the answer for question 3A, part 2.